So if you're watching this video, this is a great review for the first few topics in Unit 3, Kinetics and Energy, Equilibrium, and Acids and Bases, and those acid-base calculations, and acid-base reactions. So again, thinking about kinetics, you do need to kind of know these four factors that affect the speed or rate of a chemical reaction. These factors when you're thinking about kinetics, so think about those really quick. What would they be? Temperature is usually the first one that comes to mind. Concentration, surface area, and catalysts or inhibitors. Those catalysts or inhibitors put the reactants together in the correct orientation so the reactants can make products. And so I like to think about, again, this hill. I've brought this up to you before, and thinking about the chemicals as being like the ball on the hill. Are they high on the hill? Do they have high energy, or do they have low energy? And so that's how we use these. And so when we're thinking about water, for example, where would water be on that hill? Hopefully you're thinking it would be low energy, whereas something like gasoline that we put in our cars would be high energy. Exactly. And so you do need to know these two units to measure energy. These are the two common ones that we use. You do need to be able to convert between them. You need to know that 4.184 calories is a joule. And so a lot of times if I'm converting those, then I would either convert to kilojoules or kilocalories using that factor of 1 joule is 1,000 kilojoules. Or I'm sorry, 1,000 joules is 1 kilojoule. All right, and calories in food, of course, that is our energy in our food. Remember, those come from the big three nutrients that are in our food: carbs, proteins, and fats. And you need to know how many kilocalories or food calories are in each gram of those. Like, for example, eggs. Now, this would be a great time to get out paper and pencil and calculator and see if you can solve this problem. So go ahead and do that at this time. Pause the video and come right back. All right, how did you do? So again, it's 156 calories in those eggs. We know that that is from our combination of fat, carbs, and protein. And so I've multiplied 9, 4, and 4 by those. Then I simply substituted in what I knew. And now I'm going to solve for protein. And so how do I do that? I simply add them together and then eventually divide both sides by 4 and get 14.03 grams of protein in those two eggs, which are why people eat eggs, because they're so high in protein. And like I said, you do need to be able to convert between calories and joules or kilocalories and kilojoules. So take a moment and see if you can do this conversion. All right, how did you do? So I like to just convert back to calories. Then I can convert my calories to joules and joules to kilojoules. And so I get something like that with two significant figures. All right, and so thinking about energy again, you do need to know how energy is involved in these chemical reactions and how much time takes place. Again, that time and rate of reaction is what we call kinetics. And so just making sure that you know where each thing is, the reactants and the products, your activation energy, and any energy given off by or absorbed by that reaction. Again, this is an exothermic reaction. So how about this one? What would you say this type of reaction is? If you were saying exothermic, you're exactly right. How about this one? Endothermic? Yes, exactly. The next topic in our Unit 3 is equilibrium. Now, equilibrium is kind of like balance because in chemical reactions, again, reactants make products, but then sometimes products can make reactants. And so these will happen simultaneously until the reaction reaches equilibrium. And so most chemists if they're working as a chemist, are going to be working on messing with the balance of an equilibrium reaction, forcing the reaction to make products. And that's pretty much what equilibrium is. You do need to be able to write equilibrium expressions. So take a moment with this reaction right here and see if you can write this equilibrium expression. So how did you do with writing this reaction? The equilibrium expression. Hopefully you only included the aqueous chemicals in there. Solids and liquids are not included. And hopefully you use those coefficients to square and multiply that by 6. All right. And so as we're thinking about these equilibrium expressions, and don't worry, I've got another one coming up for you, and I will send you a bunch of equilibrium practice. And so this idea is named after the French chemist Le Chatelier, and in his principle that at equilibrium, the reaction will respond to stresses that are placed on it. The 3 stresses are concentration, pressure, and temperature. All right. And so what we have to do then is practice writing some of these equilibrium, or practice looking at this reaction. Once again, my arrows did not come up. I tried something new here. So here is this equilibrium expression, SO2 reacting with oxygen to make SO3 and heat. So if this reaction is equilibrium, how would it change if we did these things? So and so if we increase the SO2, that is going to allow us to be able to make more products. So our equilibrium would shift, we would say, to the right or toward the products. If we increase our SO3, like we add more SO3, well, that SO3 then would decompose to make SO2 and O2. And so our reaction would go that way. If we warmed up the system, heated it up, in other words, we're going to add more heat. And so heat is like a product here. And so that would also shift our reaction to the left. If we removed SO2, so there wasn't much SO2 to combine with oxygen to make SO3, if we remove SO2, then the system itself will try to make more SO2. And we don't need to worry about this amount of O2 that would be needed. In a industrial situation, you would have to worry about that. And so you will just need to practice these on your own. The other thing that often factors in is pressure. And I think I've got something for you about that. Again, the 3 factors to consider when thinking about equilibrium: concentration, pressure, temperature. Keep in mind, catalyst is not on this list like it is for kinetics. And so if you change the temperature, this is how your equilibrium will change. If the pressure changes or the volume changes, think of Boyle's law. So what you would have to do is look at your reactants, count up how many moles of gas are present, look at your products, count up how many moles of gas are present, and go from there. Again, these equilibrium expressions, what they tell us is the reaction at equilibrium, making products the same rate it's making reactants? Is it are we making products? That would be a large K value. If we're not making products and we're just making reactants, then it's a small K value. Something like 0.005 is small. It's compared to 1. And so here are some shifts in equilibrium from Le Chatelier's principle. And so if you increase the concentration of the reactants, you're going to make more products. If you decrease the concentration of the reactants, you're going to make more reactants. The products will make more reactants. If you increase the pressure, it will go towards less moles of the gas. If you decrease the pressure or increase the volume, it will go towards more moles of the gas. If you increase temperature, it'll go away from the heat. If you decrease the temperature, it'll try to make more heat. And then a catalyst, again, has no effect on equilibrium. All right. And so our next topic is acids and bases. And so what do you need to know about acids and bases? Well, the first thing you need to know is, what is an acid? What are acids' characteristics? Acids, of course, produce hydrogen ions or hydronium ions. We call them the same thing interchangeably. They taste sour, have a pH less than 7, Of course, they can be corrosive because of that hydrogen ion, or hydronium ion is just like a naked proton, so it's very reactive. Bases, on the other hand, can have an OH, or they can accept a hydrogen ion. Depends if you're thinking about Arrhenius or Bronsted-Lowry theory of bases. Bases also taste bitter, feel slippery. And so, so some of my pictures are not showing up here today. I apologize for that. And so you need to be able to look at how many ions are in the solution and calculate the pH. So at my house, the pH of our water is 4.5. So how many hydrogen ions or hydronium ions, this is our hydronium ion here, are in my water? And so what you have to do in order to do that is remember that equation, pH equals the negative log of those hydrogen ions or hydronium ions. And so then what you would have to do is take that 4.5 equals the negative log of those hydrogen ions or hydronium ions. And so what you're basically doing is an inverse log. And so the way that we do this is you would take 10 and raise that to the power of the negative pH. So negative 4.5, and that will give you the hydrogen ion concentration or hydronium ion concentration. And so you will need to be able to do that. Don't forget, when acids and bases react, this is a neutralization reaction. They're going to produce salt and water in that neutralization reaction. It is true we could look at this salt and realize that this salt is also the conjugate base, and this water here is the conjugate acid. That's how Bronsted-Lowry looked at acids and bases, working in partners. All right, and so here is a great question for you to work on for neutralization reaction. So great time to pause the video and see what you can do. All right, so how did you do? Well, hopefully as you're looking at this reaction, the first thing that you were thinking is that you can't use the M1V1 equals M2V2 because you have 1 mole of base to equal 2 moles of acid. So you will have to use your solution stoichiometry skills here. All right, and so what you would have to do is take the concentration of your base and the volume of your base. I always just like to convert to liters when I'm working with molarity. In this case, you really wouldn't have had to do that to figure out how many moles of barium hydroxide are there. Then when I got my moles of barium hydroxide, now is when I have to look at my balanced equation and know that 2 moles of the acid is equivalent to 1 mole of the base. Let me see if I can pull that down a little bit so that you can see it. And that's going to give me my moles of HCl. Once I get my moles of HCl, all I need to do then, after I've got my moles of HCl, hold on, I think they're coming right up here. Then all I need to do is divide by my molarity, and that is going to give me my liters. This equation asks for it in milliliters, so it's 0.06. I've slid that right over liters, which is going to, of course, equal is going to equal 6 milliliters. All right, so those are the things that you need to know in this unit. Of course, you have your acid-base titration lab that you've done. And when you get to that equivalence point, your hydroxide ions from your base equal the hydrogen ions from your acid. Keep in mind you did use an indicator for that, and because it's a 1-to-1 ratio, you can use the M1V1 there. All right, and so here's a quick little titration one that you can use. So potassium hydroxide reacting with hydrochloric acid. So see if you can figure out the molarity of the HCl in this case, like what you're doing in the acid-base lab. Great time to pause the video and see how you do. All right, so how did you do? So hopefully one of the strategies is to kind of list and take a look at everything you know, right? And so then our formula. And I always like to write the formula, and I have written that on some of your tests that it's good to know what that formula is. So hopefully you figured out that the molarity of the acid is 1.1. Here are a couple of other practices for you on titrations. I'm not going to work these out for you, but I am going to give you the answers. So this will be a great time for you to pause the video and see what you can do on these. All right, so how did you do? Let's take a look. So that first one, again, you can use M1V1. And so hopefully you came up with 0.014 molar. The second one, hopefully you came up with 0.79 molar. The third one, 14 milliliters, because it asks for how much HCl. Okay, and so here is another one for you to take a look at. For another titration, I apologize. It looks like some of my animations are not working correctly. So as I'm looking at this, I can see that 3 moles of this acid are equal or equivalent to 2 moles of the base. And so for this one, I can't use M1V1. I have to use my solution stoichiometry skills. So what would I do? Well, first I'm going to figure out the, I'm going to use the 67 milliliters and 0.5 molar HCl to figure out how many, or molar H2SO4, to figure out exactly how many moles of H2SO4 are present. Then use the mole ratio from the balanced equation, as you can see there. Now once I figure out my moles of aluminum hydroxide, I think some of them might be in yellow there. I'm going to divide by my volume to get the molarity. And so that's the molarity of the aluminum hydroxide that I have to use. You also need to be able to look at how much hydroxide ions, how many hydrogen ions, and figure out the pH. And so you do need to be able to do some pH calculations. And of course, this is my chart that you should have with all of these calculations in it. So you can see the answers for that chart. I hope that helps you. And then again, strong and weak acids. The difference is that strong acids are producing lots of hydrogen ions. In the lab, you also made a buffer. Buffers are chemicals that resist changing pH. The way that you made it was you took the weak acid, acetic acid, and mixed it with its conjugate base, sodium acetate, to make that buffer. And so as you're looking back at your lab data, you can see how the pH of that buffer resisted changing. I hope this helps you with these 3 topics in this unit.